Hello and welcome to the third video of the M3 chapter Dynamics. No starter today because we have quite a few notes to get through. In this video we're looking at simple harmonic motion. Simple harmonic motion is a very specific type of motion. Although they don't all involve strings and springs, I'm going to use the idea of a spring to explain how this will look. So if we've got a spring at its natural length here, we add a particle on the end and we fix this end to a wall. So this is fixed, and here we've got a particle. Then we stretch this away from its equilibrium point, away from the natural length, so there's tension, and we let go. And we're assuming that all of this is going to happen on a smooth horizontal surface, so there's no friction. So as we stretch this out here and we let go, it will move back towards the center point, or the natural length, because the tension is a force acting this way, producing an acceleration this way. As it passes this point, it now has no acceleration because there's no tension at this point, but it does have speed, so it continues across here. Now there's thrust in the spring as it compresses, and the acceleration is acting this way to push it back out. So it slows down, it comes to an instantaneous stop, and then the acceleration continues to act this way, pulling it this way, and it gets to this point again with speed going this direction. And so if there's a smooth horizontal surface, this will keep oscillating like this. And the particle's speed will decrease as it reaches its maximum compression, then it will increase and it will have maximum speed going through this point, slow down as it reaches its maximum extension, increase, so there's some slowing down and some speeding up as it moves, and it will oscillate around this center point, which we call the center of oscillation here. That is simple harmonic motion. Mathematically, there are two key elements to this motion. Simple harmonic motion always has acceleration in the opposite direction to its displacement. Now that's the displacement from its center of oscillation here. So if the particle is on this side, there's a displacement here, and if we say that is a positive displacement this way, then the acceleration will act this way, which we know it does. But then when it's on this side here, and now we do something we don't normally do in mechanics, we're going to switch mid-question which way is positive. We're going to say the displacement direction is positive, and then we see again the acceleration is in the opposite direction to that. That's the first key thing. The acceleration is always in the opposite direction to its displacement. The second key thing is that the acceleration is proportional to its displacement. As the displacement changes, the acceleration changes. In this case, you can see as the displacement increases in this direction, the extension on the string is increasing, which is increasing the force, the tension, and therefore the acceleration, which brings it back this way. These two things together give us the idea that acceleration is proportional to the displacement, but in the opposite direction of the displacement. So A is proportional to negative x. Changing that into an equal sign, we have a constant of proportionality here, and we get this. Now there's a couple of things to notice here, because this might look reasonably familiar, this might look a little bit weird compared to this. First thing is this x with a double dot. I hope you remember that x with a double dot above it is referencing specifically differentiation with respect to time. And with two dots, that means the second derivative of x with respect to time, which of course you know is a. So it's just a different way of writing a, and the reason for that is because we'll have another a come into this working out further down the notes, and we don't want to get the a's confused, although I will still use a in certain situations. For example, if we have f equals ma, I'm fairly confident no one is going to mistake this a for anything else other than acceleration. So I will use this notation interchangeably with acceleration a. The other thing that you might notice here is that we've got a very strange w. Now this is an omega. You might have seen omega before in various other situations, but why on earth would I choose omega squared as my constant of proportionality instead of the usual k? normally just put minus kx here. And spoiler alert, that's something else we're going to look at later, and it's connected with the next chapter on circular motion, and the omega here is angular speed. So although it looks funny, this is still coming from this, which is coming from these two key points. The acceleration is proportional to the displacement, so there's a constant here which we've called omega squared, and it's also in the opposite direction of the displacement. So this is our defining equation for simple harmonic motion. If you see anything in this form, you can say yes, this is simple harmonic motion, and if you're told it's simple harmonic motion, you can be sure that this is true. Okay, that's great, but there are other things we might want to know about the motion of this particle. For example, the velocity and the displacement. We have an equation for acceleration, and we know that acceleration connects to velocity and displacement. We've already seen displacement here, so let's have a look at this. We have the acceleration, here it is, as a function of displacement. So to help us define the velocity, we can use a is equal to v dv by dx, if you remember your work on kinematics from previous chapters and modules, and we can integrate this to get velocity in terms of displacement x. So if we change x double dot into v dv by dx, now we separate the variables, v dv and minus omega squared x dx, and integrate both sides. V squared over 2 is equal to minus omega squared, because that's just a constant, x squared over 2 plus c. Now here we need to be a little bit careful. This plus c is very important, because when x is 0, v is not 0. If we go back for a second to the previous screen, at this center point here, the center of oscillation, when the displacement from here is 0, the speed is at its maximum. It's not 0. The speed is 0 when the displacement is at its maximum. So we'll have the maximum displacement, and at that point the speed v is 0. So that's what we're going to use here, and we're going to call the maximum displacement a. This is that very a that is easy to get confused with the acceleration. There is a reason for using a, we'll come back to that in a little while. So we're saying at maximum displacement from O, the center of oscillation, we know that the speed at that point is 0, and we're going to call x a, where a is the maximum displacement from O. So this bit here, this hasn't come from anywhere, we're defining that this is what it's going to be from now on. So using that, we're going to say 0 squared over 2, obviously that's 0, is equal to minus omega squared a squared over 2 plus c. So when v is 0, we're going to let x equal this thing a. That gives us a c value of omega squared a squared over 2, and we can put that back in to here to get the equation of v squared over 2 equals minus omega squared x squared over 2 plus omega squared a squared over 2. Multiply everything by 2 to get rid of those fractions, and factorize out omega squared gives us v squared equals omega squared a squared minus x squared. So this is a function for the velocity of the particle with its angular speed omega, whatever that is based on the situation we've got, times by the maximum displacement, and that will be given to you in the question, or something that you find in the question, minus the displacement from O at the point you're looking at. So if the displacement from O is 0, you're at the center of oscillation, this collapses back to v squared equals omega squared a squared, and that's your maximum speed. But if x is equal to a, at the maximum displacement, a squared minus a squared is 0, and this collapses down to v equals 0, and you get 0 velocity at the maximum displacement. So that's all self-consistent with what we've said so far. This is a very useful equation. It's going to come up here on the next screen. Here it is up here, along with the acceleration statement. Now we can continue this, because we know that velocity is dx by dt, so we can put that in here and integrate again to get displacement as a function of time. So our starting point here is where we left off on the last one. So if I square root everything here, we're going to have omega square root of a squared minus x squared is v. Change that v into dx by dt, which you could call x dot, but we're about to separate the variables, so there's no point doing that. Bringing the square root over here, I'll change that into index form. So we've got a squared minus x squared to the minus a half as it comes onto the left is equal to omega dt on the right. And then we integrate, and we realize that actually this is not a standard integral. It's not that easy. To do this, we will want a substitution. Let's have x is equal to a sine theta. Differentiating that will give us dx is equal to a cosine theta d theta. Putting those in gives us the integral of a cosine theta d theta over the square root of a squared minus a squared sine squared theta. And of course on the right, omega dt. Quickly looking through this, we're going to factorize out a squared and have 1 minus sine squared theta, but 1 minus sine squared theta is cos squared theta. So this will become a squared cos squared theta. Square root of that will be a cosine theta, and of course we have a cosine theta on the top. So if we simplify all of that with some trig, we get a cos theta over a cos theta d theta, which of course is suddenly very nice. And we get the integral of d theta is equal to the integral of omega dt, giving theta is equal to omega t plus c. Now I have to change theta back into x, of course. Looking back over here, if we want theta, we're going to have to do the inverse sine x over a is sine theta, so theta is equal to the arc sine of x over a. Putting that back in over here, arc sine x over a is equal to omega t plus c. Rearranging this to give x as the subject, we're going to have to do the sine of omega t plus c, and that will give us x over a, so we multiply by a, and we get x is equal to a sine omega t plus c like this. Now to link up with what the textbook says, I'm going to use an alpha here instead of a c. So this is a function for the displacement of the particle at any given time. If we know the displacement, we can then find out the velocity. If we know the displacement, we can also find out the acceleration. So we have a lot of information here now. These are the three key things worth remembering. And a quick note, depending on the starting point of the motion, we can simplify this a little bit. This displacement one here, the awkward plus alpha here, doesn't always have to be there. Because if we have motion starting at the center of oscillation, then we can put in a boundary condition there, where at t equals 0, x equals 0, that's the center of oscillation there. So if you follow that through, you end up with alpha equals 0, so the displacement function collapses to this. If the motion starts at the end point of the oscillation, then alpha, if you put in the boundary conditions t equals 0, x equals a, the maximum displacement, the end point, then you will work out that alpha is equal to pi by 2. But if alpha is equal to pi by 2, we know that sine theta plus pi by 2 is the same as cosine of theta from trigonometry work long past. So you can change that into x equals a cosine omega t. On the one hand, these are much simpler because they don't have this pesky alpha in the way. On the other hand, you might not mind the alpha being there if it means that you only have to remember one expression. Regardless of which ones you use, so long as you use them in the right way, they will all give you the same answer. And it is really important to remember that regardless of which one you're using, regardless of where your motion starts, x here and x here are both still the displacement from O. They're not the displacement from your starting point. So if you start at the end point, that's great, you can use this slightly simpler expression without worrying about alpha being pi by 2, but your x, your displacement value, is still x measured from the center of oscillation. So it can get a little bit confusing. You need to be very clear about what you're using and where you're measuring from. Quite a lot of notes, there's still a few more. One quick note on the period. Regardless of whether we use this expression, or this expression, the period of oscillation is still going to be 2 pi by omega. Now the period, if you remember back to your sine and cosine graphs, the period of the graph is one full cycle. Usually that's 2 pi, where this is sine of t. But if that's a function of t, and we think about our transformations, if we do f of omega t, then we've done a multiplier inside the brackets here to get a multiplier on the t here inside the function, like this. And what that does is to stretch the graph by a scale factor 1 over omega. So if omega is 2, for example, then we get this. And suddenly we've got 2 cycles in 2 pi, which means the period, which is one full cycle, is now half of what it was just at pi. So you can see here, if omega is 2, then the period is half of what it was divided by 2. So as omega increases, the number of cycles you get in 2 pi increases, and the period of one cycle decreases by that scale factor. So that's why the period of oscillation is this. And of course, plus alpha here has no effect on how many cycles you get in one section. It's just shifting the graph left or right along the x-axis. So that doesn't matter if there's a plus alpha there, the period is still this. A, which we've been calling the maximum displacement from O, now has a reason why we've defined it as A. And that's because it's the amplitude of the graph. Again, thinking about transformations, if you put a 2 times in front of this, you get 2 sine t, and you know that that doubles the amplitude, like this. Okay, I would say that this also is as important as these in terms of remembering key equations, that the period is 2 pi over omega. But the next slide is a little bit more information that's useful, but might not come up in every example. Simple harmonic motion is closely related to motion around a circle. Of course, it's a bit annoying, circular motion doesn't come up until chapter 4, but one of these has to come first. So there's a bit of a sneak preview here for chapter 4. If a particle travels around a circle at a constant angular speed, which we call omega, and that's why we've got omega here instead of just a regular k. And before I finish that sentence, let's just quickly talk about that. So if we start here, and let's make it fairly easy, let's say pi by 4 radians in 1 second. So we move pi by 4 radians in 1 second. Then in 1 second more, we've moved another pi by 4. 1 second to here, 1 second to here, 1 second, 1 second, 1 second, 8 seconds in total. So this motion is constant. The change of angle in a given time is constant. That's what omega is, radians per second. And if that's true, if it's traveling around at a constant angular speed, then the x-coordinate of the particle shows simple harmonic motion along the x-axis, and the y-coordinate along the y-axis does the same. And you can see that if we move from here to here, pi by 4 radians, then the x-coordinate, let's draw a few of these out, the x-coordinate here, we've done 1 second here, 1 second to move this distance on the x-axis. We also do 1 second to go from here, so in another second it's moved all the way over here. That's a much bigger distance. So for the same time period, we've moved a bigger distance. Obviously that means it's going slower here, faster here. Another second, we're over here, and that's over here, symmetry. And then another second, it's at the end. So if you can imagine this particle's traveling around at a constant angular speed, the x-coordinate of this particle is speeding up through the center here, and then slowing down, and then coming back as it comes down, coming back, speeds up through the center and slows down. And you can see that there's simple harmonic motion here. And also with the y-axis, the y-coordinate will be doing this with simple harmonic motion as well. So simple harmonic motion and motion around a circle are almost the same thing viewed from two slightly different perspectives. And we can prove that this is simple harmonic motion by showing that this equation holds true. So here if we've got x, we know that the radius of a circle is r, and this angle here is theta, but in terms of omega, I said omega is radians per second, so the angle, radians, is omega times time, so that's equal to omega t, which we'll look at again in much more detail in chapter 4. So theta is equal to omega t, then r cosine of theta is equal to x, the x-coordinate of this point up here, p. So that is equal to r cosine of theta, which is omega t, and if we put that over here and then differentiate it, we get x dot, so that's dx by dt, we get r omega cosine goes to minus sine omega t, and then if we differentiate it again with respect to t, we get x double dot minus r omega squared cosine omega t, and this, the r cosine omega t, is equal to x. So we do, if we replace that, indeed get minus omega squared x for the acceleration. Okay, that was a lot of notes. Key points to take away. These three equations here. The fact that this top one is a defining characteristic of simple harmonic motion. If you need to prove it's simple harmonic motion, this is the equation you're trying to get to. This one, very useful if you've got the speed or if you need the speed. This one if you're looking at the displacement or the time. And this one, when I use it in the examples, probably won't have plus alpha if we're starting at the center. I just won't use it because it will be 0. If we're starting at the edge, I will probably change it into a cosine so that I don't have to use the alpha there as well. The fourth thing I'll be using a lot of is the time period. T is equal to 2 pi over omega. So I think in terms of calculations, these are your key things. In terms of proving simple harmonic motion, this top one is your key thing. The rest is nice to know, helpful to understand, but not as useful in terms of actually solving problems in the exam. So let's have a look at a few examples. A particle is moving along a straight line with simple harmonic motion. The amplitude of the motion is 0.8 meters. So that is telling us from the center of oscillation out to the extreme edge, the end point of the oscillation is 0.8 meters. And in the other direction, it is also 0.8 meters. So there's a total length being traveled here of 1.6 meters, backwards and forwards. It passes through the center of oscillation O with speed 2 meters a second. If it passes through the center with that speed, whichever way it's going, 2 meters per second is our maximum speed. So we've got some useful information here. We know that A is 0.8, that's this A here and here, and we know that the maximum speed is 2, so the speed v here is 2 when x here is equal to 0. Calculate the period of oscillation. Okay, if we want to know the period of oscillation, that's our capital T, 2 pi over omega, so we need omega. To find omega, this equation here I think will be the easiest because we know A and we know V is 2 when x is equal to 0 from this information here. So we've got V squared is equal to omega squared, A squared minus x squared. V is equal to 2, we don't know omega. A in this question is 0.8, and at V is equal to 2, that happens when x is 0. Solving for omega gives me omega is equal to 5 over 2, and the units there is radians per second. From there we can find t just by doing t is equal to 2 pi divided by 5 over 2. It gives me 4 pi over 5 seconds, which is 2.51 to 3 significant figures. So that is the period of oscillation. Now let's be clear here, oscillation, like a sine curve, is a full cycle of motion. So it's here, to the end point where it stops for a moment, comes back through here to the other side, stops here, and returns back to here. So it's a full cycle, this, back, and this, and back. That takes 2.51 seconds. Part B, find the speed of the particle when it is 0.4 meters from O. Okay, now we know omega and we know A, we can use this here to find V at any given point. Here we've got 0.4 meters from O, so if x is 0.4, we can find V using this equation. So we've got V squared is equal to omega squared, which we now know is 5/2, A squared, which we already knew was 0.8, minus x squared. So we can put in at x is equal to 0.4 meters from O. This is important. This is always going to be measured from O. So at x is equal to 0.4, we can find V. 25/4, 16/25 minus 0.4 squared. And that gives us an answer of 3, which seems nice, but then we have to square root it. So V is equal to the root of 3 meters per second, which is 1.73 to 3 significant figures. So that is the speed as it passes through point 0.4 meters from O. Now the time the particle takes to travel to that same point, 0.4 meters from O, is going to be using the bottom equation here. We're given x is equal to 0.4, we know A, we know omega. I'm not worried about alpha because starting the motion here, alpha is 0, and then I can find t by rearranging this equation. So part C, squeeze it in here. We've got 0.4 for x is equal to 0.8 for A, sine of omega, which we know is 5/2 times t. Rearranging this, we get t is equal to the inverse sine of 0.4 over 0.8, and when we do that, we then multiply by 2/5 to get t, and that gives me the answer pi by 15 seconds, which is 0.209 seconds to 3 significant figures. Example number 2. A particle P of mass 0.5 kilograms is moving along a straight line. At time t seconds, the distance of P from a fixed point O on the line is x meters. The force acting on P has magnitude 10x and acts in the direction PO. Show that P is moving with simple harmonic motion. Okay, as soon as you get a question like this, proving or showing that you've got simple harmonic motion, this is the equation you're aiming at. So to get something in this form, whether or not you know the constant omega squared, doesn't matter, so long as you can say it's in this form, it will be simple harmonic motion. So let's work with what we've got. We know the force is 10x and acts in the direction from the particle to O. So it's acting towards O. So we've got a line like this. Let's put O in the center here, the center of oscillation. P is over here somewhere. As it's moving, it's acting in this direction, and when it comes over here, as part of its motion, it's acting in this direction. So the force here is 10 times x, but if we've got x as a positive displacement, then the force is actually equal to negative 10x. If we're calling the displacement OP positive, then the direction of the force PO is negative. We also know that F is equal to ma. Here's one time where I'm using A as acceleration, not amplitude, and that is equal to what we've just said, minus 10x. Now immediately, to try and avoid confusion, I'll change that A into x double dot. So we've got mx double dot is equal to minus 10x, and I think writing it like this makes it very clear for the examiner what I've done. Now I need to put in the mass. I know the mass, 0.5. 0.5 x double dot is equal to minus 10x. Divide through by that, and we get x double dot is equal to minus 20x. And that's it. This is in the form this, where we know omega squared is 20. I don't really need to state that outright, but I should make some sort of concluding comment. Even something as simple as therefore SHM. and the examiner will recognize this as simple harmonic motion. So you can save yourself a few seconds of writing that out. But I quite like to say this is of the form x double dot is equal to minus omega squared x, with omega is equal to square root of 20. Therefore, simple harmonic motion. I don't think you need this bit here, but my point here is that you should put something. Don't just leave it there. You should make it clear to the examiner that you understand this is enough to say, yes, I've got simple harmonic motion. So that's part A. Part B, find the period of the motion. Well, now we've done this, we know omega is the square root of 20. This is quite easy. We just need to use period is equal to 2 pi over omega, where omega is the square root of 20. Which is root 5 pi over 5, or 1.40 seconds to 3 significant figures. Next example. A particle is moving in a straight line with simple harmonic motion. Its maximum acceleration is 12 meters per second squared, and its maximum speed is 4 meters per second. Calculate the period of the motion. Okay, we've already talked before about maximum speed. That is the speed when x is equal to 0. That's very useful for this equation here. But maximum acceleration we haven't really talked about yet. Maximum acceleration happens at the very end point of your motion. If I go back to the spring again to explain this, the spring with the particle on the end, as you extend that out to its maximum extension, the end point of the oscillation, that is where the tension in the spring is at its maximum, pulling it back towards the center point. So having a maximum force in this position is what gives us a maximum acceleration through F equals ma. But we have to be a little bit careful because acceleration is always given as a negative in relation to the displacement, and we've been given a positive here. So really what this is telling us is that the absolute value of minus omega squared x is equal to 12. Or if you wanted to write it as minus omega squared x is equal to minus 12. Whether you think of it like this or like this, we get the same starting point here of omega squared x, where x is equal to a is equal to 12. Sorry, I guess that should have been a there as well, because this is happening at the maximum displacement from O. So this was telling us at x equals a, x double dot is equal to 12, or the magnitude of this is equal to 12. Back to the maximum speed, we said that is telling us at x is equal to 0, v is equal to 4. Using the other equation gives us 4 squared is equal to omega squared a squared minus 0 squared, so 16 is equal to omega squared a squared. Now we can put this equation with this equation and find a and omega. If I divide this by this, we get a is equal to 16 over 12, so a is 4 over 3. Putting it back into this equation to give me omega, we get omega squared is equal to 9, so omega must equal 3. This gives us our period. T is equal to 2 pi over omega, which is 3, so that's it, 2 pi over 3. Or if you prefer decimals, 2.09 seconds to 3 significant figures. Part B, the amplitude of the motion. Well, I've already done that. That seems strange that they're asking for that afterwards. I guess you could solve these two for omega first without finding a, but that seems a little bit strange to me. Anyway, we've already done that. Part C, the length of time during one complete oscillation that the particle is within 1/3 of the center of the oscillation. Okay, I know I drew a spring here to represent that, but we are not told it's a spring. It's just a particle moving on a straight line. So let me redraw this. We've got the center of oscillation here, and we know A is 4 over 3. So this is 4 over 3 in this direction from here, and then we have another 4 over 3 in this direction from the center of oscillation O. We know it takes about 2 seconds to do one full oscillation, and we want to know the length of time during one full oscillation that the particle is within 1/3 of the center of the oscillation. So 1/3 is about here, and on the other side about here. So as the particle starts here, comes out this way, slows down, comes back, speeds through here, slows down, comes back to its starting point, how much of that time is spent in this section here? So there's a little bit as it goes out, and then it goes up and back, and then there's a little bit as it comes back through, and as it goes out this way, and then there's a final bit as it comes back through the end here. So if I can find from here to here, because of the symmetry of the motion, I can just multiply that by 4. 1 on the way out, 1 on the way back, 1 on the way out this way, 1 on the way back. So all I really need is the time it takes to get from O to 1/3 of a meter away from O. And that's a time question, so we're looking at this expression on the bottom here. So at x is equal to 1/3, we get 1/3 is equal to a, 4/3, sine of omega t, and we're starting the motion at the center here, so I'll use alpha is 0 again, so we've got omega, which we know is 3, times t plus 0, they cancel, so we get the inverse sine of 1/4, and then we have to divide that by 3 to get time, and that is 0.0842 ... So the time I actually want is 4 lots of t, and that is 0.337 seconds to 3 significant figures. And that's the time it spends within 1/3 meter of O during one full oscillation. 2 examples left. This one, a small rowing boat is floating on the surface of the sea, tied to a pier. The boat moves up and down in a vertical line, and it can be modelled as a particle moving with simple harmonic motion. The boat takes 2 seconds to travel directly from its highest point, which is 3 meters below the pier, to its lowest point. Now that's not one full oscillation, so be careful, this is not the period. The maximum speed of the boat is 3 meters per second. Again, that's telling us when x is 0, v is 3. Calculate the amplitude of the motion. Okay, I'm going to draw this out a little bit, because we've got something funny happening. We've got a pier, and then there's water off the pier with a boat on the water. But we're told the highest point is 3 meters below the pier. So if we go down 3 meters from the top of the pier, this is the maximum point, the highest point of the motion. And then it goes down to wherever it goes down to, let's say here, with the center of oscillation in the middle. And it takes 2 seconds for the boat to travel directly from its highest point to its lowest point, which is only half of an oscillation. So the period, that's enough information to say, is 4 seconds. And we know that equals 2 pi over omega, so that is enough information for us to find omega. Omega is equal to pi by 2 radians. So using v squared is equal to omega squared, a squared minus x squared. At x is equal to 0, v is equal to 3. So we've got v squared, 9, is equal to omega squared, pi squared over 4, times a squared, which is what we're trying to find, minus 0 squared. That gives me a squared is equal to 36 over pi squared, so a is equal to 6 over pi meters, or 1.91 to 3 significant figures. Part B. Calculate the time taken by the boat to rise from its lowest point to a point 5 meters below the pier. Now, that's actually quite awkward, because we've got 3 meters below the pier here. 5 meters means another 2 meters, which is just a little bit more than the amplitude. So we've got another 2 meters here to give us a total of 5 meters below the pier, and that is just this side of O. And that tiny distance there is 2 minus the amplitude 1.91, or what will be more helpful, I think, is to keep this as a nice exact amount. This little distance here is 2 minus 6 by pi. So the displacement from O is this, and the displacement from O connected with time is this equation here. Now here's one of those slightly confusing things, because the time taken by the boat to rise from its lowest point is starting at the end point. We're not starting this motion at O for this question, we're starting from here. This is one case where I would use a cosine omega t. But the x, the displacement, even if we use, if I write it out, x is equal to a cosine omega t, even if we use this expression to start our considerations from here, the x is still measuring from the center point O. So I'm still using this distance in this expression, but because we're using cosine instead of sine, it will give me the time from this point to this point. If that's too weird for you, you can use this expression with alpha equals pi by 2, or you could continue to use x equals a sine omega t and measure from this point in terms of time to this point, and from this point to this point, and then find the difference between the two, and that would give you the time from this point to this point, which by the symmetry of the motion would be the same as the time from this point to this point. So there are different ways of doing this if you have a preferred version of this formula here to use. For the sake of showing how to do it, I will continue with this one here. So we've got x, 2 minus 6 over pi, is equal to a, the maximum distance away, 6 over pi, cosine omega, which we know is pi by 2, times t. So if I manipulate this slightly, pi over pi there, cancel this, we get 2 pi minus 6 over 6, and we can do the inverse cosine of that to get pi over 2t, so t is 2 over pi times this. Putting all of that on my calculator gives me the answer 0.9699 ... So to three significant figures, 0.970 seconds for t. Final example. A particle P is moving with simple harmonic motion along a straight line. The center of oscillation is point O, the amplitude is 0.6, and the period is 8. Okay, we've got a fair amount of information there. We know A is equal to 0.6, T is equal to 8, which is 2 pi over omega. Therefore, omega is equal to pi by 4 radians. The points A and B are points on the line of P's motion and are on opposite sides of O. The distance OA is 0.5, so it's not the end point. 0.6 is the end point. And OB is 0.1, that's quite close to O. Calculate the time taken by P to move directly from A to B. Okay, I think a diagram will help us here. So we've got the endpoints here, center of oscillation here. A is 0.5 meters away, let's put that here, and B is 0.1 meters away on the opposite side of O from A, so that's about here. So this distance is 0.5, and this distance is 0.1, and we want the time it takes to go from A to B. Now I have to be careful to realize that although this distance is 0.6, same as this distance, the time from the endpoint to the center is not the same as the time from A to B, because this bit here that we're not using is the slowest part of the motion, and this bit here which we're using instead is some of the fastest. So as we shift from here to here, the time is very different even though the distance is the same. To find the time then, what I would do is simply split it how it's naturally split here. What is the time it takes to go from O to A? What is the time it takes to go from O to B? And then add the two together. And if we want to know time, and I want to know it from here, let's use this equation here with alpha equals 0. So I'm using x is equal to a sine omega t. I'm going to use it twice, once to get this, and once to get this, and then we'll just add them together. So at x is equal to 0.5, we've got 0.5 is equal to 0.6, which is a, times sine of omega, pi by 4, t. So t is equal to the inverse sine of 0.5 over 0.6, and when you've done that we then multiply 4 over pi. At x is equal to 0.1, very similar, 0.1 is equal to 0.6, sine of pi by 4t, so t is equal to 4 over pi inverse sine of 0.1 over 0.6, and then let's call this t1 and t2, and then the total time is equal to t1 plus t2. Putting that on my calculator, we find t1 is 1.254 ... and t2 is 0.213 ... Adding them together gives me a final answer of 1.47 seconds to 3 significant figures. And that's the final answer. Quite a long video there. I hope that's enough for you to have a go at some of the questions in exercise 3C, and we'll start the next video with a simple harmonic motion exam question. Maybe I'll see you there.